Okay, so we will start now. Welcome to the day 3 of our course on scientific computing on GPUs with OpenACC. So today, before we start, let's see what we did previously. So last day, we discussed different memory models, which included the shared, distributed, and the heterogeneous memory models. We discussed what different hardware types correspond to these different memory models. And also, we discussed different programming approaches for these types of systems. We discussed a little bit in detail OpenMP, and we also touched upon MPI and OpenACC. We will cover OpenACC properly today. As we said, this correspond to different memory models. Before I continue, I am audible. Just can someone confirm?
Yes, you're audible.
Okay, thank you. All right. So as I said, we discussed a bit of OpenMP and we looked at the API document, which has all the details. Why we discussed this was because it was very similar. It is very similar to OpenACC syntactically, and it will be helpful for us. So agenda for this week, again, this week only today there is class. Tomorrow, since Diwali, will not have class. So this week we will look into some extra motivation for OpenACC. We will see how to get started and how we can install a supported compiler using NVIDIA HPC SDK. During the starting of the course, if you remember, we said that we'll be using NVIDIA GPUs, and therefore, for the best optimized results, you should be using a compiler from NVIDIA. And we will see how you can install such a compiler. We will look at the OpenACC execution model, as how, if given a problem, how you can execute it using OpenACC, and we will look at some of the basic compute constructs. Okay, so let's look at some of the motivation for using OpenACC. It is directive based, as I said the last day, just like OpenMP, so it is very familiar to users. So if you know OpenMP, you know 50% of OpenACC, as in how you need to program it, you will know it. And it is easy to use for non-CS and other domain people. What do I mean by this? Like people who are from a different background, like myself. I am actually from the physics background, and I have learned to do GPU programming using OpenACC. After that, I have slowly picked up a little bit of CUDA and other things. But to get started, if you drop somebody who has no experience directly into CUDA or OpenCL, it will be a bit difficult for them, and it will take them time to learn it and then apply it to their domain. For example, I am a PhD student and I have to solve some physics problem, right? Using some programming. I have to do some simulation or something. But like if I have to first learn CUDA, then learn how to do the programming and then do it for my system, it will take a long time. So OpenACC helps in such scenarios where the learning curve is very small and it is very easy if you know OpenMP. And we do not need to write device specific code like CUDA. As I said, CUDA is from NVIDIA and it will only run on GPUs from NVIDIA. And in some cases, it might be that somewhere you have access to a GPU machine, somewhere you might have access to a AMD GPU machine, somewhere you might have access to no GPUs, so you have to run on CPUs. So if you write CUDA, you will be stuck with machines which only has NVIDIA GPUs. In other cases, you cannot. But OpenACC is open, like it can be run on CPUs and all different kinds of GPUs like NVIDIA and AMD as well. And it gives what is called incremental parallelism. What does that mean? It means that we start from a serial code. Let's say that, okay, let's say that you have some serial code ready. You are solving some problem in your PhD or whatever you are doing, and you have written a code which is not parallel. And you have to now convert it so that it runs using GPUs and multi-core CPUs. In that case, if you have to use CUDA or OpenCL, that serial code is useless for you. You have to again go back to the drawing board and write it from scratch pertaining to the standards of CUDA or OpenCL. But using OpenACC, just like OpenMP, you don't need to do that. You take that serial code and you look into the portions which take a lot of time. Mainly for applications, most of the time is taken in loops, most likely, and some functions, complicated functions and things like that. So what you can do is, let's say your problem or the serial code you have written has 5 loops. So you will start with the first loop, you will first parallelize that. Then you will see how much speed up you have got. Then you will parallelize the second one, so on and so forth. So you can do it incrementally. You don't have to throw away your serial code and write some new code from the beginning. So this way it is very easy, especially for non-computer science people like myself, or some of you might be here from other backgrounds, so that you do not have to throw away your serial code. You can start from there and incrementally get parallelism. Okay. So before I go on, I'm curious, how many people are here? I'll just put a poll, like how many people are here from a non-CS background? I mean, you can just write down in the chat or something. I have just put a poll, just vote. I would be curious to know. Okay, anyway, so, all right. Now we will see how to install the NVIDIA HPC SDK. So this is one of the ways to get one compiler. So as we know, if you write a code, you need to have some compiler to compile it. GCC supports it, but as we saw that this is a very NVIDIA specific thing, so it will be good if you can get the compiler from NVIDIA. So first you have to check that you have a GPU. That one we discussed the first day. You can check by lspci command in Linux. Then you have to see if you have your GPU drivers properly installed. How to check that? You have to put the command nvidia-smi in the terminal. If you put this command, if your drivers and everything is updated properly, you should see an output which looks like this. See, I have put NVIDIA SMI here and it is showing some output. This is the screenshot of the terminal. You can see that it is showing that I have one GPU which is called Quadro P620. It is showing all the details, like it is running at 43 degrees centigrade temperature. It has 2 GB memory, out of which 400 megabytes is used. Nothing of compute is running, so that is 0%. And it is showing which processors are running on the GPU. So you can see Cinnamon is running because I use Linux Mint, Xorg is running, and some other thing is running, and these are running in graphical mode. So here if you see type, here is G means graphical, and if you run some compute, which we will do a bit later, maybe in the next class, here C will come. So G means graphical, and if C is there, C means compute. So you should get an output which looks like this. So that will show you if you have a GPU, and if you have a GPU, if your drivers are properly installed. Okay. If not, if you don't have this and if you don't get this output, you have to install the drivers from NVIDIA's website or the driver manager of your Linux distribution. And that is recommended because it will give you the driver version which is properly compatible with your hardware and OS. So you have to do this. Next step is you have to go to NVIDIA HPC SDK download page. The link is given. I will show you the web page. You have to go there and accept the license agreement. Something is there. Anyway, it is a free software. It is provided by NVIDIA for free. And you have to select whichever OS you are using. People generally use Ubuntu, Linux Mint, and things like that. For them, this last one is okay. You can choose this one. And if you go there, this one I will show in the website because it is easier. So you see, this is the website where it will be available. And if you go, you have to go to this download now. If you go to this download now, yeah, you have to accept the license agreement here, and they will show you these two options. And this is Linux x86-64. This is for most of you, probably. I don't think anyone is using Power System here or ARM servers here, and some of you might be using Windows. But then they say that HPC SDK for Windows will be available at a later date. So I think the best way to get it is use Linux, and there are two versions. You can get the latest CUDA version here, or you can get the version which has three previous CUDA versions along with it. So you will probably use this. So there are these instructions. So one by one, you open a terminal and execute these instructions. So it will install it from the internet. You update your system and you will just install in NVHPC 23.9. So you just follow these instructions and it will be installed. You just have to copy and paste these instructions into your terminal. Okay. And upon successful installation, you can either every time go in and compile in the binary folder of the installation, or you can add the path /compiler/bin, that is wherever you have installed the thing, to your path in the bashrc file. This is a very common step and you can look it up. And to see if it is working, you have to run the command pgaxlinfo. If you run pgaxlinfo after this, you will get some output. I'll show you that. And the compiler is named pgcc, just like GCC, but with a P. And if you want to use the C++ compiler, you have to do pg++. So yeah. The output of pgaxlinfo, if you have properly installed it, will look like this. Again, it is showing the same information. This is in my machine. I have a Quadro P620 GPU, and it will be showing you how much memory you have, how many multiprocessors you have, so on and so forth. All the extra details are not really required for you right now, but this is how the output should be if you have installed everything correctly. Okay. Maybe after this class, you guys can try it out. Like whoever has a Linux machine and has an NVIDIA GPU, you can try it out and see if this works. Okay, now let's look at the OpenACC execution model. Like how do you have to write your program? Swarnim Maheshwari is asking which method should we choose? Which method are you talking about? Can you clarify?
Actually, I was talking about that tar, and like there were several methods.
Okay.
Yeah, apparently I'm getting an error. The command not found.
What is your OS?
It's Ubuntu.
Ubuntu. Okay, it's saying override command not found. CUDA multi. Okay, we will look into this a bit after the class. Okay.
Okay, okay.
Yeah. All right. Swarnam, can you turn off your mic? Okay. Yeah. All right. OpenACC execution model. What do I mean by this? So it is like you have to write your program in some way. You have to think about the algorithm. So these are the properties. So it is host directed. What does it mean? That the execution is controlled by the CPU. You might be executing on the GPU, but the execution is controlled by the CPU. So let's look at this figure. This will explain what it means. So there are, you can see two lines I have drawn, one in red and one in blue. This blue one represents the CPU and the red one represents the GPU. So the program starts executing from the CPU only. You will run the program on the CPU. You cannot directly run the program on the GPU. The CPU has to instruct the GPU to run something. Okay. Now, first you start and you have to do some setup. Let's say you are doing some problem which you are facing in your research or something. You have to set up some matrix, some array, something. You have to first set up all that on your CPU. So you see these red boxes and blue boxes which I have drawn. This means there is some execution on the CPU. This, for example, this light blue box here, it means we are executing some code on the CPU. And this light red box which I have drawn here, it means there is some execution on the GPU. Okay. So first we set up everything on the CPU, like how many arrays you need, how much memory you need, what, so on and so forth. You have to first set that up on the CPU. Then you transfer the data onto the GPU. Or if you don't have to transfer data, what you do is you do a kernel launch on the GPU. So this arrow means you are now giving the control to the GPU. Now there are two types. We will come to that. This example on the first part is where when GPU is executing, CPU is not executing something. For example, like something might be there for which you need the results from the GPU execution so that it executes after that on the CPU. So in that case, your CPU has to wait. So over here, when GPU is executing, there is no execution on the CPU. So this part is blank. After GPU finishes, it has calculated some result, something. The control is given back and the data is transferred back to the CPU. And then the CPU starts executing. It will probably use some data or result which is calculated in the first GPU part. This is one type of execution. But there is also another type of execution called asynchronous execution. We will come to its examples a little bit later today. But there is asynchronous execution. What is that? That is showed here. Your CPU is executing, like from 1 you have returned here. You have got back whatever data you want and so on and so forth. And your now CPU is executing. Now let us say after this point, there is some calculation you want to do on the GPU, which is here, but the CPU calculation is not dependent on it. So what you can do is you can start this calculation on the GPU and you can carry on whatever you are doing on the CPU as well. So you see, I have not stopped the execution here. My CPU execution is also going on. My GPU execution is also going on. Therefore, this is called asynchronously they are executing. It's sort of, they are executing parallelly on both CPU and GPU. And since there is no need for a data transfer, because as we said, this job might be independent of what is the calculation being done on the GPU. There is no data transfer or any transfer back here. So this thing ends here. Let's say this GPU part ends here and the CPU goes up to this. Then again, it might be that we need some job, some GPU execution, which is dependent on the CPU, and CPU cannot execute beyond that before this GPU job finishes. So again, we transfer control and data here. It executes on the GPU on this part, and it again comes back and it ends. So what we see here is it is being controlled by the CPU. Like from CPU, you are giving the instruction to the GPU. It starts executing. CPU can decide if, as in you will have to decide what the CPU will do. So you can decide either you want to wait for the GPU to finish or you don't want to wait. So again, it is all being controlled by the CPU. And if you don't want to wait, you can asynchronously execute something and then again wait for the GPU to come back for some other calculation. So basically this is the way. Like you have to think, like if you have some algorithm, you have to think which parts can be done on the GPU, and also you have to think while doing that part, can I do something else on the CPU? So this is the way you can execute this. So this is the execution model and it is host directed. So CPU has to do all the things. It has to instantiate and allocate GPU memory. Like it has to instantiate how much memory on the GPU. It has to transfer the data to the GPU memory, like I have shown it the blue arrow here. It has to start the GPU execution. After GPU execution finishes, it has to again take all the data back to CPU memory, that is RAM, and then finally deallocate memory on the GPU. This deallocation is very important, otherwise you can have something like a memory leak, like you can start accumulating something on the GPU memory and you can have something like a memory leak. So deallocation is also important and CPU has to do that separately. And as I said, CPU and GPU may execute asynchronously. Okay. Now the CPU may queue various operations on the GPU. What do I mean by that? So in this figure, this one line I have drawn, I have marked it as GPU, but then there could be many such lines in a single GPU itself. Like you could have within GPU, you can have different queues. So what do I mean by a queue? Like this is Q0. It is pushing one kernel to the GPU here. It might push, if there was another line like this within a single GPU, that is what is a queue. And all of these have multiple queues. All GPUs have multiple queues available. And you can push different jobs, which can again then be executed asynchronously on the GPU itself. So you can have multiple queues within the GPU. Then there can be more than one queue. And for most purposes, like the whole premise of this course is mostly scientific computing and numerical methods. Most of the things we do involve loops, as they form most of the compute intensive parts of the numerical methods and scientific computing applications. Loops are the most important. You need loops for searching, sorting, things like that. So loops, and then if you are doing something numerical like integration, doing something like ODE solving PDEs, things like that, everything needs loops. So we target loops most and see if we can parallelize them on the GPU so that we can get a bit of speed up. Okay, so this is the execution model. Up till here, does anyone have any questions before I go on to the other things? Okay. Now, let's go on to the basic compute constructs. Just like OpenMP, if you remember that day's class, in OpenMP, what we had done was we had used hash pragma OMP parallel for. Similarly, as I said, these two things are very similar. In this one, you use hash pragma ACC parallel, and in clauses, you have to put something like loop, something. So we will come to those, what we can put in that clauses. There is another one called ACC kernels. Kernels is something like a bit of magic, but we will come to and see what does it mean. And there are a few other hash pragmas as well. These are compiler directives. These are like hints to the compiler so that the compiler which you will use can automatically generate the GPU code for you. By the way, this compiler which we downloaded and everything, and we are using OpenACC, after all, what will happen is it will translate the code, whatever you are writing, to CUDA. So we are anyway going to CUDA. So you must remember that. And that will become apparent once you see the compiler output. Then, as I said, loops are the most important part. So this is one basic code which I have written, the very popular Hello World code. And we have stdio, like what we do, and int mains. Now, this for loop will go for 10 iterations, I equals to 0, I less than 10, I plus plus. And I have printed hello world inside it. And I have put the iteration number I in the print statement. And I have put hash pragma ACC parallel loop. Hash pragma ACC parallel is the first part, and loop is the clause which we have used. Since we have to target the loops, can somebody guess what the output here will be? Anyone?
Since these are all executing in parallel,
Yes.
the order is not going to be in order, right? So it's just going to be hello world, some random number, then hello world, random number.
Okay. Anyone else? Anything? Okay. Swarnim, you are correct. So let's see the output if I run this. Okay, before even I go to the output, let me show how you first compile this. See, I think this is visible. To compile this, you have to give the command pgcc. I had named the file pair1, so pair1.c. dash O is the output file name, dash TA equals to NVIDIA. This is where you are saying your target architecture is NVIDIA, since you are using a NVIDIA GPU. Dash ACC means accelerate. This is one flag you have to use. And dash M for accel means it will show you which portion has been accelerated. So if you see correctly, in the compiler output, it is saying generating NVIDIA GPU code, pragma ACC loop gang block IDX. So what is happening is, in line they are saying in line number 4, 1, 2, 3, 4, there is a loop and they are generating NVIDIA GPU code for it. Sometimes these line numbers vary depending on what spacing you have used and all, but more or less you can understand from this output if your loop has been parallelized. So you see it has written generating NVIDIA GPU code, and what Swarnim said is correct, that the order becomes jumbled up, 840291537. If there was hash pragma ACC parallel loop was not there, it would have been 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But in this case, since it is parallel, randomly it will print. Parallel means everything will get executed in parallelly together. So it will get jumbled upon. Like if you run this code multiple times, this sequence might be different. Not like if you run this particular code on your machine, it might be that you get that sequence of numbers to be different. And that is what is expected. What does this teach us? This teaches us two things. That first of all, okay, our parallelization is happening and it is executing in parallel. That all is fine. But the other thing is, you will not be able to guess the sequence in which it is executed since it is parallel. Therefore, you have to be careful that whatever calculation you are doing should not depend upon the sequence of execution. So printing hello world 8 and then 0 and then 4 is fine. But if you are doing some calculation where your iteration 0 must happen first, and if you parallelize that, you will be in problem. So you have to identify what type of loop you can actually parallelize. So you have to keep this in mind when you are using this. So it's not like you just randomly write hash pragma ACC parallel loop without thinking anything and it will work. You have to make sure your iterations are not dependent. Okay, so the next thing we use a lot is something like a nested loop. Nested loops are used in sorting and like other things like matrix multiplication and many other things. Some nested loops are used. Two loops you have. So what I have now written is hash pragma ACC parallel loop I equals to 0 to 5, and then inside that I have j equals to 0 to 5 and I have printed hello world ij. Now what do you think the output of this one will be? I would point out I have put parallel loop only on the outer loop. That hash pragma I have put only on the outer loop. So what do you think the output of this will be?
I think even though the order of the first loop will be jumbled up, the order of second loop will not be jumbled up.
Correct.
So it will be like 5, 1, 2, 3, 4, 5, then 6, 1, 2, 3, 4, 5, and 10, 1, 2, 3, 5, like that.
Yes, you are absolutely correct. So again, let's look at the first look at the compilation output. So again, it is saying generating NVIDIA GPU code. Since we have put ACC parallel loop, then it is saying ACC loop gang. This gang and everything I will come to in the next classes. What does it mean? But it is saying that there is a parallelization happening using the gang. But the next loop, ACC loop, is sequential. So one loop is getting parallelized, one loop is not getting parallelized. So that is again evident from the output. If you see what Swarnim said, that the J loop you see is always happening together. Like ith is getting jumbled because ith has been parallelized, and for one I, you can see like the j 0 0 0 0 0 1 1 1 1 1. So whichever index you have parallelized, that is going to get jumbled up. That is the parallel loop, nested. Okay. Now let's see if we do this. Hash pragma ACC parallel loop on I, hash pragma ACC parallel loop on j. What you would expect? You would expect both to work, isn't it? Let's, Swanim, what do you think? Okay, but as it turns out, this will not work because the output is, it will not compile only because nested parallelism is not supported. So you have to do something else. And this is a restriction by the compiler. I think this will be removed recently, and so that such nested parallelism can be done. But till now, at least the compiler version I have, nested parallelism is not supported. I'd have to look in if the recent compilers have removed this, or the recent OpenACC standard has removed this. But the current version does not allow it, which I have with me. So right now, no nested parallelism. So, but then you actually can do something, and you can do something called a collapse. And loop collapsing is a common idea. Like if you have two indexes, you can, like this is basically indexing using two variables. You can convert that to a single index, and this collapse thing works. And you have to write hash pragma ACC parallel loop, and you have to write collapse. And in bracket, you have to give how many loops to collapse. And what type of loops can be collapsed? It can only be collapsed if the loops are tightly nested. What is meant by tightly nested? That the two for loops should follow each other. Like one for loop is here, and the next for loop begins right after that. There is no statement in between. So such loops can be collapsed, and you will get some output. And I will show you the thing. If you see, generating NVIDIA GPU code, hash pragma ACC loop gang vector 32, this vector I will come, and it has collapsed it. Okay, now as I said, kernels is bit like so what we learned from the previous thing. If you are targeting loops, by the way, this loop thing will work for while as well. So while loops, if you are using and you have a fixed number of iterations, then this will work if you use while loops as well. I have not shown this here, but you can try it out. And again, as I said in the beginning class, that all this works for Fortran as well, if you are going to use Fortran. The only slight difference will be the syntax will be slightly different. It will be using something else, but the concepts are the same. Okay, now if you are going to use kernels, what is kernels? Let's say you don't have time, like this example is very simple, like the two for loops are there, what is there? But your algorithm might be very complicated, and it might be very long, and you just don't want to trouble yourself with going through each loop, checking whether it is parallelizable, checking what you have to do, checking if you need to do something else. You don't want to go into all that issue. You just want to the compiler to do whatever it can. That is where kernels come in. You will have to put whatever code you think could be parallelized. It might not, it might be, it might not be. That is up to the compiler's intelligence. But you want your code to be somewhat parallelized, and you want the compiler to do it automatically. You don't want to go into every loop and do it separately. That time you will use hash pragma ACC kernels. Now what will happen? If you use kernels, you see that I have not used parallel loop, but again, it has generated the same thing. That it has generated collapse, it has shown that the loop is parallelizable, it has generated GPU code, things like that. So kernels is like a bit of, you are giving the compiler freedom to check if something can be parallelized, nowadays compilers are very intelligent and they can figure out if something can be parallelized, something can be not. Is somebody saying something? Okay. Yeah, so compilers are intelligent and they can actually figure out what you have to do. So this is sort of like magic, and you can ask kernels to do it for you if you have a big code or something. Now, let's come to the scenario where there are two loops. Like in the execution model I showed you, there are different GPU executions. So you might have one loop which is I equals to 1 to 0, I less than 10, I 0 to 10, I plus plus, and hello world 1. And then you have another loop which prints hello world 2 with the iteration variable. And on both of them, like before, I have put parallel loop, and they are not nested. So they are completely different loops. So what do you think will be the output? Can anybody guess?
The first loop will complete, and after that, the second loop will start. So
Correct.
they will execute in series. The
Correct.
loops themselves will get executed in series.
Yes, and this is exactly the same what was there in OpenMP. If you remember, in OpenMP there was a question towards the end, like if there are multiple things, will they be executed in parallel? And as I said, you have to put no wait if you want to ask them to execute in parallel, but otherwise they will execute one by one, and that is what happens. So first you see hello world 1, 80426, whatever is coming. So hello world 1 is here, and then the iteration things are mixed up. It is mixed up because it is parallel. Once 1 finishes, only then 2 will start. Then hello world 2 comes, and then it goes again from 4, 8, whatever it is. You see the order of the iterations is different within the same code itself. So it is fully random, and you don't know how you can control that. So again, as I said, you have to be careful that your execution should not depend upon the order of the iteration. Only then you can parallelize. So this is the case. If you have two loops, what will happen? Okay. Now, it might be that your work which you have, it's like you want to execute something on CPU as well. So let's look at the next example. The next example is like, let's say there is some work on the GPU, but as in the example I showed you in the diagram before, that let's say you want to execute something along on the CPU as well, parallel to the GPU. It is anyway executing parallel to in GPU directly, but you want to execute something on the CPU at the same time. So for example, if you see this, I have given I equals to 0, I less than 10, I plus plus, printf hello world 1. Then I have given some print statement saying between worlds 1, and then after that there is another for loop. So, and if you now notice, there is another clause here called async. So let me first show the output, and then I will explain what is happening here. Okay, if you see this, the output here, output says between worlds 1. In the code, what has happened is this code is here first, but still between worlds, which is in the second part, I mean after this for loop, is getting executed before that. Why is that happening? Since there is async, what the control is doing is when it encounters this, it is pushing it to GPU. It is sending it to GPU. But otherwise, if there was not async, it would have stopped there until it finished execution. But in this time, async is there. So the CPU will go on. CPU will execute the next statement which is available, which is printf between worlds 1. Now, you might say that it should execute in parallel, but what ideally it should have, but what generally happens is since that instruction that to execute this loop, this first for loop on the GPU has to be sent to GPU, the GPU has to start up and things like that, because GPU start up, it has to allocate memory, everything is there. So by the time that happens, hello between worlds 1 is printed. Now the thing will start, between worlds 1 is now printed. Then that loop comes. That loop starts executing. And 1111 is there. Then it reaches parallel loop. Then 2222 is there, and then it prints between worlds 2. This is very important. Asynchronous execution will be very important for us, since this is where the power of GPU will come, that you are executing in parallel on GPU, and then you are going to execute something to not waste time, that you can do some other computation as well, right, on the CPU as well. This is a very basic example using Hello World, but when you are doing big calculations, this will become very important, that you have to be able to think asynchronously. So what we generally do in programming, we first execute this loop, then this loop, then this printf command. In this case, it will not happen like that. And this is very important. And this between worlds 2 comes at the end, because after this loop, there is since there is no async here, the control will wait here for everything to finish, and only then after that it will execute between worlds 2. I have put an extra ACC wait, but this was not needed, but yeah. So I will show you what is the effect of ACC wait in the next slide. I hope this part is clear, and this is very important for our applications. Now, there are two, now again, it is the same code I have put here, but now both of them have async. What is happening here? This is again very interesting. First one, this loop has been pushed to the GPU. It has executed between worlds 1 in the first place. Then this loop is also async. What will happen? This will also get pushed. And then it will print between worlds 2. This is also now printed between worlds 2. Now, since GPU will start up, take a bit of time, then again, this has now gone into the queue. If you remember, I have talked about a queue there. This loop is now first in queue to get executed. So 11111 gets executed first. Then this one is now in the queue to get executed. Then 2222, it will get executed. These two executions ideally will happen in parallel with the CPU, but then due to limitations of the speed and all, this between worlds 1 and between worlds 2 comes first. And I will wait here. If this wait is not there, it will become a problem. What problem will it become?
It will go to return 0 and exit.
Correct. So I have put async hello world 1. I have put printf between worlds 1. I have put a wait here. Okay, that wait which was here, I have now put it here. And then I have put ACC parallel loop async and hello world 2 and then between worlds 2. And what he said is correct. This is what happens. So first this loop is sent to GPU, and then hello between worlds 1 is printed, and I wait here for this loop to finish. So it finishes. So this loop has now finished. Then I push the second loop to GPU. It has now gone to GPU, and I have printed between worlds 2. But I have not given the wait here. This wait is here, and it immediately exits. And therefore, even if this loop has now gone to GPU, and it will not be able to execute because my program has exited. So this is where the concept of wait, like if you are going to do asynchronous programming, you have to tell the CPU to wait, otherwise it will just go on. So in such a scenario, you have to ask the CPU to wait, or this loop will not execute. I hope this is clear, and this is very important, because see what happened, there is no compilation error. Your program just executed. Ideally, what should happen is there should be some compilation error saying this loop will not get executed or things like that, but it does not say that. It just simply does not execute. Even if it is there, it will not execute and it will just end the program. So this is actually very important to keep in mind, that if you are going to use async, first of all, async you can do, like you can execute something on CPU and GPU parallelly. And if you are going to use async, you must give wait in proper places so that the CPU does not go out and go into some other calculation. For example, what happened here is it returned 0 and it ended, but in some situation there might be some other calculation happening, and that calculation's value depends upon this for loop. So in that case, there will be some error. Like if there was another for loop which was dependent on this for loop, and this for loop has not executed, in that case, there would have been a problem. Okay, so before I end today's class, we are a bit early, but is there any questions from this part? Because this loop part is very interesting and very important for us. Okay, Swarnim is saying, but kernel did not parallelize the second loop. Okay, let's see that. Hello world. Loop 6 is parallelizable, 8 is parallelizable. ACC loop gang vector 32 collapse 2. Okay, so from this output, it might look like that it has not even parallelized the first one, isn't it?
Actually, there is like a lag between your screen and our screen. So,
is it okay now?
yeah, it's fine now.
Okay. So yeah, if you look at this code and if you actually look at the other code, like where I had shown the collapse, it might look like that it is actually not parallelizing the first one also. So it looks like that, but internally, if you look at the GPU execution, it has parallelized. In this case, I tried it many times, but it was actually coming in sequence, mostly because if you are collapsing, it will just create a single index and do all the iterations, but it is actually parallelizing. It might look like it is not, but if you see the GPU output, like the compiler output, you can see that it is actually parallel. They have actually generated GPU code.
Can you like do a time test to like?
Yeah, so yeah, I understand, but using this example, time test is not meaningful. So I think it will only be meaningful when we do examples like matrix multiplication. Okay, this is just a small iteration. Again, yeah, this is important. Like if you do small iterations, like I have done some 5 iterations in the previous example, there were only 10 iterations and things like that. If you do that, small iterations, GPU will actually be slower than your CPU. Why? Because as you saw, when you're doing async and everything, the GPU starting up, copying the data and things like that takes a bit of time. So if that time is large in general compared to the execution time. So if you are not using a large number of iterations, and we will do that in the later, maybe while you are doing the numerical methods part, if you are doing that, then only you will see when you have a large number of iterations, you will see that there is some advantage. For small iterations, actually, if you are going to execute this code, which I am showing on screen, using only CPU, and then you time it using that, and you time it on GPU will probably be slower, and it will be slower. So yeah, you have to. So these examples are just for illustrative purposes, but yeah, so you should use large number of iterations.
Also in previous class you told that like while loop cannot be parallelized because the number of iterations.
Yeah. That is for OpenMP. If you look at the OpenMP, what was there, it will be hash pragma OMP parallel for it was. Okay. That is specifically used for loop in OpenACC. See, these are all dependent upon the implementation. If you are, there are certain while loops, like if you are going to do int n equals to 0 while n is less than equal to 10, n plus plus. Okay, so in such loops, you can actually use while. So we can go into this thing. Yeah, we can again, OpenACC also has their specs. So if you can look into the specifications, like I am showing on screen, and I will look at the loop construct. So you can use loop construct for both things. Let's see if they have given examples. Okay. I think you can use it for while also. I cannot find it immediately, but as far as I remember, I don't use the while loop that much, but while loop is also parallelizable if the number of iterations you are doing is predetermined. Like the example I gave, like if you have a int n equals to 0 while n less than equals to 10, and if you do a while loop for that, it will be parallelized. In OpenMP, if you use hash pragma OMP parallel for, in that you cannot. But okay, I will check up for the example for while loop and maybe post it in the group. Okay, and yeah. So we today looked at these loop things, and loops will be the most important thing we use in our numerical methods part, because we will do examples like integration, ODE solving and things like that, where loops will be very important, and mainly we'll be using for loops. So this will be important. And today we have not used any data, like we have not used any array, like we have not used examples like vector addition, matrix multiplication. So those will be important, and for that you need to use something called the data handling. So data handling we'll be covering in the next class. It is almost 3 o'clock today, so let's see what we'll do in the next class. So we will next do data handling and data transfers. Like as I said the day before, that CPU and GPU memories will be different. So if you are going to use a matrix or an array which you will store in some CPU memory, you have to copy that. We looked at a bit of asynchronous processing, and we will look at more examples like how to implement different queues. That is also important. And then we will look at a bit of multi-GPU programming. So that if you have 2 GPUs, 4 GPUs, how you can use that. So this will be the agenda for next week. Tomorrow, Sunday, it is Diwali. So I don't think, so we will not have a class tomorrow, and we will meet on 18th November. And well, happy Diwali to all of you. So tomorrow you guys enjoy. We will meet next Saturday. Now let's look at the problem. Happy Diwali, sir. Yeah. That's fine. Let's look at your problem. Like if others wants to stay, it is fine. Maybe we can see why your thing is not executing. So you installed maybe can you share your screen and show us like what this problem is happening? Swarnim, are you there? Yeah. Okay, you have a GPU. Okay. Now you have tried curl. So in front of that curl, okay, that is fine. GPG, no valid open PGP found. I think there is some wrong. Okay, by the way, do it one by one, not all of them together. Execute each command one by one. Go to the website. And
Yeah, actually, yeah, I will do that.
yeah, okay, maybe others can try it out as well, so that if you have any problems, we can solve it.
This is the first code.
Yeah. Yeah. Do
That's
this.
better.
Do the second one. Yeah.
This.
I think this should work now. It will update. Is this a laptop or a desktop?
This is my custom-made desktop.
Okay. Okay.
Okay, so it seems to be done working fine now.
Yeah. Yeah. And if you execute the next command, it will take a bit of time. Okay. That is like some huge, I think 8 GB of thing it will download. So it okay, no, not 8 GB. It is downloading around 25 GB. So it will take some time. So you have to be a bit patient. Okay.
Okay. Thank you for that.
Yeah. Yeah. Yeah.
There should not be like much difference between like copying pasting the command like as a whole and individual, right?
It should not, but I don't know. Sometimes it is a bit weird. I'm not sure. It should not be, but I'm not sure.
Right. Thank you, and yeah, happy Diwali to you.
Okay. Okay. Others, I think you should try out. And if you have a system where you can install this, I think you should try it out.
Sir,
Yeah.
so I tried this. First, I tried installing NVIDIA utils. Like because NVIDIA SMI was not found, so it was suggesting to install with NVIDIA util.
Huh.
NVIDIA, but after that also it is saying SMI has failed because it couldn't communicate with NVIDIA driver. Make sure that the latest NVIDIA driver is installed and running.
Okay.
So
You have a yeah. So you have a Ubuntu machine or a Linux machine?
yes, Ubuntu.
Okay. Swarnim, maybe you can close your screen sharing.
Stop.
Yeah. Can you share your screen now?
Yes, sure.
Yeah.
So I had started with this.
Okay. Wait. This is Ubuntu, right?
Yes.
Have you just scroll down? Like, show me your terminal. Like, what is the last output?
This one.
Okay. You have a AMD device, correct?
Yes, yes.
Then NVIDIA SMI will not work.
Okay. Even I was.
Yeah. So do something. First, let's see. Can you just do sudo apt install GPU stat? GPU stat.
GPU
Stat STAT.
STAT.
Now write GPU stat once.
It is saying unable to locate. What should I do?
Oh, it is saying unable to locate. Wait, let me just check once then. GPU stat. Okay, it might be the issue. I'll have to check. But again, NVIDIA SMI won't work because it is this thing.
Yeah, AMD. Yeah.
So, all right. But still, I think you can still install OpenACC because that is supposed to be independent of NVIDIA or AMD.
Okay.
But yeah, you can try that out. But other than that, I don't see any way to help you. See, all
So, okay, so with the normal, like in general OpenACC, I can at least try with the basic, like this, whatever is going in class, right?
Yeah, that you can try. So what you have to do is you have to execute it on CPU. So I showed today -TA NVIDIA, right? So
Yes.
to execute on CPU, what you have to do is -TA equals to multicore. So if you do that, you will it will actually execute in parallel, but on the CPU. So everything will be the same. As I said, everything is the same, but that data transfer part won't be there. Apart from that, it will be the same.
Okay. Yeah. Okay, sir. Thanks.
This is your laptop probably, right?
Yes, yes.
Okay. And okay, then it's 3 o'clock. So I'll close the meeting today, and we will meet next Saturday to discuss some other examples, and we will take it from there. Thank you, everyone, and happy Diwali.